we're building up a table that says, okay, here's a bunch of rules for how to do Laplace transforms of various functions. Every time we're going to be meeting for the next couple sessions, we're going to be like, okay, we're going to add a rule. Just to say we're going to broaden our horizons. And so last time we added a couple of rules. So in particular, last time we talked about the rules down here in this corner. So that is, we looked at the function u sub a. And so what is u sub a? It's the unit step function, also sometimes referred to Heaviside function in a few places. And essentially it's something which it's an on-off switch. And the idea is at time a, we go from 0 and jump up to 1. And so I like to think of it as, oh, something happened at time a. So you're essentially turning on a piece of the function. So this is really great if you have piecewise functions. And so we're going to use that when we explore piecewise functions. And sort of the moral of the story was there's this extra little piece up here, this e to the minus as. And last time I made a vague statement that says, oh, if you start seeing things e to the minus as in your Laplace transforms, that really means that there's this unit step function is involved. And so we're actually going to make that more precise. So every day we should add a rule, right? So today's rule is we're just going to extend what we did before. So today's rule. If we have u sub a of t and multiply it by a function f of t minus a, and we take the Laplace transform of that, that becomes e to the minus as times f of s. And remember, our convention is f of s is what happens if you just took the normal Laplace transform of f of t. So the punchline is we should think of e to the minus as, if we see that showing up on the side where we've taken the Laplace transform. So after the Laplace transform, if that shows up, we're like, oh, something happened. There was something that turned on at time a. So that's how we're going to think of that piece. Now we should justify this. And the way we justify a rule is we go to the definitions. So let's actually run through the definitions and verify that this is what we claim it to be. So we'll take the Laplace transform of u sub a of t, f of t minus a. By definition, integral 0 to infinity, e to the minus s times t, and then what we're taking the Laplace transform of, u sub a of t, f of t minus a dt. So we just have to figure out what is that. Now, we've talked about this u sub a. We have a picture of it here. And in particular, what does that mean is happening to this expression before time equals a? It's 0. So u sub a says, look, everything that happens before time equals a, I'm going to be 0. So it's going to zero out the whole thing. So what we can do is we say, okay, instead of starting at time 0, where should we really start? At time a. So we're going to change that 0 to an a, and then say, look, you can now get rid of that part. Say, okay, well, that's something. Now we say, let's clean it up a little bit. And we'll do it by substitution. So this t minus a, we'll call that tau. And we're going to go through and update our integral. So everything now is going to be in terms of tau. So tau is the new t. So we can start with the bounds. Our bounds used to go from a to infinity. Those were with respect to t. Now where will we go between? So if t equals a, what does tau equal? 0. And if t equals infinity, what does tau equal? Now some people might say infinity minus a. Well, that's still infinity. You know. So our bounds shift from 0 to infinity. That's a good sign. E to the minus s something. I'll come back and fill that part in. F of t minus a becomes f of tau, because that's how we're choosing our tau. What's dt become? D tau. Okay, everything's looking pretty promising so far. There's one last slot, because I have to replace all the t's. So what will this t become? Tau plus a. Now is our little aha. We say, hey, you can distribute the minus s through, and then you can also break it up. Because if you have an exponent where you have addition or subtraction upstairs, it breaks up into multiplication. So you have e to the minus s tau, e to the minus s times a. This has nothing to do with tau. Meaning we can treat it like a constant, pull it out. So you pull it out. I'll just rewrite as e to the minus a times s, so that's pulled out. Integral 0 to infinity, e to the minus s tau, f of tau, d tau. And now we look at this and say, that seems pretty familiar. What is it?
It's the original Laplace transformation.
It's the Laplace transformation of just the function itself. And that's what we call f of s. And there's our justification. So our new rule for the day. If we see e to the minus as, that tells us that something got turned on at time a. And in particular, what's the something? Well, you say, okay, what's the Laplace transform of the piece it's attached to? And just make sure you shifted it so that it starts at time a. And we'll get some practice with that, not today, but in the very near future. The other thing we talked about is we can now talk about Laplace transforms of derivatives. And so the nice thing is when you have a derivative, essentially you add in a factor of s. So first derivative, you'd have s. Second derivative, you have an s squared. But you also have a little bit of a correction term. And so the full statement is when you take the Laplace transform of f prime, it's s, f of s, and subtract what happens at f of 0. Laplace transform of f double prime, s squared f of s minus s f of 0 minus f prime 0. So attached to the f of s, however many derivatives you took. So one derivative, two derivatives. If you can imagine if I took a third derivative, it'd be s cubed. And then just your powers are going to go down. S squared, S1 in this case. Here, S1. And finally, your pieces start at f of 0 and they go to higher derivatives. So f0, f prime of 0, so forth and so on. All right, so those are some things we're going to need. Okay. Well, don't worry. We're going to add more to our table. And probably at some point today, we'll need to look at our table again. So what are we talking about today? Well, we're going to spend a chunk of time talking about partial fractions. Now, if you've had Calculus 2, you might be looking at this and saying, this feels really familiar. And that's because I just went and grabbed the Calculus 2 lecture notes and I cut and pasted. This is Calculus 2 lecture notes. Now you might say, so we're just reviewing Calculus 2 stuff. But actually, partial fractions isn't even calculus. It's algebra. And so what is partial fractions about? Well, the goal of partial fractions is to say, let's learn to pull expressions apart. Because it can be tricky. There's people who will look at something like 1 over, say, x squared plus x, and they're like, oh, hey, here's an idea. 1 over x squared and 1 over x. And a couple of you are like, yep. Let me write that down. What's the problem? Yeah, it's not true. It's hard to break stuff in the denominator. Now, numerator is beautiful. You have addition upstairs, you break it up, you're just happy all day. Denominator is hard. So you might say, okay, well, is there anything that can be done? And the answer is, well, yes. It turns out x squared plus x can be factored. It's x times x plus 1. And you can check, it's not trivial to check this, but it doesn't take a lot of time, that it's the case that 1 over x times x plus 1 is 1 over x minus 1 over x plus 1. This is true. So this is always true. So somehow we were able to make something simpler by pulling it apart. And this idea of pulling apart, this is partial fractions, where we are able to pull things into parts. And, well, really, we should say our goal is to put things into simpler parts. Because, well, that's how math works, right? You take a hard problem and make a slightly less hard problem. And if you do that often enough, it might even become doable. That's the goal. That's the goal. So how does it work? Well, it starts with a nice observation. It says every polynomial, and here we're going to think of s as the variable, because that's what we see in Laplace transforms. You can factor it. So we're thinking in particular, when we talk about our polynomials, these are our polynomials in the downstairs part, the denominator. We factor it. And there's pieces will look like s minus a number, or they'll look like s minus a number squared plus b squared. So this is what we call irreducible quadratic. Irreducible quadratic means you can't factor it further without having some sort of complex piece showing up. Okay. And so our goal is to say, all right, we want to take this expression, which has a lot of stuff in the denominator, and pull it apart into little pieces. Each piece we can handle. So how do we do it? Well, if we see something in our denominator which looks like s minus something to a power, then we say we're going to have pieces that look like this. A constant over s minus something plus a constant over s minus something squared. And we're going to keep going until we get to our s minus constant to a power. So we just build ourselves up. And these numbers, a1, a2, ak, are something. They're constants to be determined. If we have irreducible quadratics, similar thing, except upstairs it's not just a number, it's what we call linear. So constant s plus a constant. But again, you have these b's and c's you need to solve for. So you have the a's and the b's and the c's you have to solve for. Now, there's a nice fun fact. It's one thing you can use to help check to make sure you've done your partial fractions form right, which is to say the number of things you have to solve for is equal to the power of your denominator you started with. If you have more or if you have less, something is wrong. But the important part of partial fractions is getting the right form. And that comes from just following these rules. If you follow the rules, you'll get the right form. We'll do a little bit of practice today. The rest of it, this is the fun part, this is what people often think of when they think of partial fractions, is solve for the constants. Solve for the a, b, and c. And how do you do it? Well, you look for facts about these coefficients. And so what you really have is you say, all right, let's start with the two sides. Clear the denominator. So this is a really important idea. And the way we clear a denominator is we multiply by something to help us so that there's nothing left in the downstairs. So we get to polynomial equals polynomial. And now we say, well, when are two polynomials the same? And you have this generic idea. Two polynomials are equal if, and you fill in the blank. Well, step one, I shouldn't say step one, possibility one, says, hey, two polynomials are equal, the same, if the polynomial's coefficients are the same. So it says, hey, look at the coefficients. Expand both sides, group coefficients, the coefficients have to match. And that helps you set up equations to solve. The second idea, this is the one that most people like, says, hey, two polynomials are the same if they always agree. Okay. So, pick good points. As your parents would say, make good choices. Make good choices. And you might say, how do I know if I've made a good choice? Well, 0 is your friend. Choose things to make lots of zeros. If you make lots of zeros, what happens is most of your pieces drop out, and now instead of having maybe 5 or 6 things you have to solve for, you have 1 or 2. And that helps you make things simpler. We want things to be simple. Now there's a third option, which is not as commonly used, which says, hey, two polynomials are the same if their derivatives match. Now, that's not so clear how do you use that, but it turns out if you are doing some partial fraction decomposition of this form, where it's the polynomial over s minus a power to the k, that turns out to be a really nice, clean way to get the answer. We probably won't have time to get to that example today, but if we don't get to it today, next time. Okay, so the plan, we have polynomial over polynomial. We figure out the right form, clear out the denominators, solve for what these constants have to be. Now, for all those fans of partial fractions, and I know there must be some out there, what did we miss? What did we not mention today that is oftentimes associated with partial fractions? Not natural log. I know it's been a long time since we've talked about this. Long division. Now, do you have to worry about long division? And the answer is no. You'll never have to worry about long division. And you might want to say, what? Why? What's so magical here? And it's not just because we're nice to you. You know, yes, we're nice to you, but there's actually a more fundamental reason. And what it comes back to, I don't have anything to point to, so I'll point to empty space right now. But what it comes back to is if you think about what should be true for f of s, okay, so here it's like f of s, what it looks like. When s is large, e to the minus st, for s large, what should that be? Should be small. And so in particular, for a very large s, this piece is so small that it causes the whole integral to be small. So what should be true is that as s goes to infinity, your expression should go to 0. And so that's why you should only work with things where the denominator has a larger power than the numerator. So that's why you don't have to worry about long division. Okay, so time for practice. Practice is good. Find the partial fractions decomposition of the following. Oh, look at this lovely thing. 10s cubed minus s squared plus 10s plus 9 over s squared plus 1, s minus 2, s plus 1. They even factored it for us. That was nice. Cool. So, where do we start? Well, we start by saying, what's the right form? So this is going to be equal to something. What will it be equal to? Well, let's just say how many pieces will there be on this side? We'll start with that. 3 pieces. 3 parts. What's in the denominator of the 3 parts? Yeah, the denominators are going to be these pieces. We're trying to break it up so it's something over this part, something over that part, something over that part. So, something over s squared plus 1, something over s minus 2, something over s plus 1. What goes on top of the s squared plus 1? as plus b. Because this is that kind of example where it's a quadratic. You can't break down further. How about the s minus 2? C. How about the s plus 1? D. And you'll notice we have 4 things to figure out. What's the degree of the denominator here? 4. That's a good sign. Okay, so the first step is what we just did. We get the right form. So in the partial fractions decomposition, it says we can rewrite this expression, which is, we call this a rational function, polynomial over polynomial, as these pieces pulled apart. What's the next thing for us to do? Clear the denominators. Now, the nice thing is it's pretty much automatic what you need to do. You say, what's in the denominator here? And now you multiply both sides by that amount. So you multiply both sides by s squared plus 1, s minus 2, s plus 1. On the left-hand side, what will be left? 10s cubed minus s squared plus 10s plus 9. In other words, what's left is the numerator. The right-hand side, slightly more interesting. Okay. What will be left with the first piece? So the as plus b, and then the s squared plus 1's cancel, and yeah, so s minus 2, s plus 1. Well, how about the second piece? There'll be a c, s squared plus 1, and s plus 1. The s minus 2 is canceled. And the last part, well, it'll be d, and then what else? S squared plus 1 and s minus 2. All right, so now we have polynomial equals polynomial. These two have to match. Using that, we have to figure out what are a, b, c, and d. So, which method do you like to use? Make zeros? So let's make good choices. I like making good choices at the start. If it doesn't work, I switch to something else. That's the great thing. We have options. So we're not like locked in. But making zeros is a nice idea. So what are some choices that help us make zeros? 2? All right, so let's plug in 2. 10 times 2 cubed, 80. 2 squared, 4. 2 times 10, 20, and plus 9. Okay, when we plug 2 into the first piece, what do we get? 0, because of the s minus 2. See, that's why we chose 2. It wasn't just random. What do we get here? 15, right? 2 squared plus 1 is 5. 2 plus 1 is 3. 5 times 3 is 15. And then forget the c. So 15 times c. The last part? 0. See, this is great. By choosing a good choice for s, we got down to an equation with only one thing we don't know, which means we can actually figure out the thing. 80 plus 20 is 100. Plus 9 is 109. Subtract 4 gets us to 105. So 105 has to equal 15 times c. So what does c need to equal? 7. We're already a fourth of the way done. That's great. Just means 3/4 to go. All right. Any other good choices we can make? -1? All right, let's make that choice. Okay. -1 cubed. Yeah. So it'll be -10. -1 squared. And -1. 10 times -1 is -10. Oh, very negative here. And plus 9. All right, the first term will go to, second term will go to 0. Last term will go to, so 2 times -3 is -6, and then the d, -6 times d. Okay, -10, -1, -10, that's -21. Plus 9 means -12. Equals -6 times d. What does that tell us about d? D should be 2. Okay, any other good choices? 0. Now you might be saying, 0 is not going to make lots of things go away. It does make one thing go away, the a times s. But what else can we do? Well, what do we know about c now? 7. So even if it doesn't go away, it's okay because it's not an unknown. And d, similar, is 2. Okay, so 0. All right, what does the left-hand side become? Nice, 0. You're awesome, 0. Okay, the first term. We'll get b times -2. So minus 2b. So, or if you can like, not 2b. Okay, how about this next part? We'll get 7. 7 times 1 times 1. The last part? We'll end up with -4 because it's 2 times 1 times -2. Okay, well, 7 minus 4 is 3. we can move that over to the other side. 6 should equal negative 2b. So what does that tell us about b? B is negative 3. Wonderful progress. Now what?
S equals I.
S equals what?
I.
I. How about, what don't we know? Yeah, so what can we pick now? We could pick anything. We could pick 100. We could pick 17. But what word should we probably pick? Yeah. Oh, you guys are so good. You've mastered the art of math. If you have a choice, you pick 0. If you don't have that choice, you go to 1. Those are your first two go-to numbers, 0 or 1. Now you're thinking like mathematicians. Okay, on the left-hand side, we're going to get 10 minus 1 plus 10 plus 9. Because 1 is very easy to plug in. Equals a minus 3 times what? Good. Minus 1 times 2, negative 2. Plus 7 times what? So 7 times 2 times 2, 28, right? 7 times 4, 28. And the last piece will be what? So 2 times minus 1, minus 4. Now, 10 plus 9 is 29. Subtract 1 means that this is equal to 28. Well, that's very convenient, because we also have another 28. Pew! Those go away. So, we can move things around. We can say 2 times a minus 3 equals negative 4. So what does a minus 3 have to equal? Negative 2. So what does a have to equal? 1. All right. And so now we're basically done. But to finish it off, we say we've solved for a, b, c, and d. So our final answer, the partial fractions decomposition, is this expression, but with the right choices for a, b, c, and d put in. So we will have s minus 3 over s squared plus 1 plus c, which we solved, oh, there it is, 7 over s minus 2 plus 2 over s plus 1. So that is the partial fractions decomposition. All right. Good. Good. Any questions? No? All right. Now, you might be saying, why are we doing this again? It's been a while. So, there's a plan. And we finished with this plan last time. So here's the plan. It says, hey, if we have an initial value, ODE, so ordinary differential equation, we can use Laplace transforms to solve it by carrying out the following steps. So step 1 was to say take the Laplace transform of both sides. And we do that, we use the tables. We don't use the definition, we use our tables. And in particular, there's the rules to help us handle derivatives. After we've done that, we solve for what we'll call capital X of x, which is the Laplace transform of what we're looking for, x of t. Say, all right, now we have the Laplace transform of what we're looking for. The challenge is, what is it? And that's where partial fractions comes in. So we simplify the expression to the point where we're able to use the tables. Now, the tables are great for things that show up in in partial fractions. So we have things like, we know how to handle s minus c to a power, for instance. And we also know how to handle things like s minus c squared plus b squared in the denominator. So these kinds of things we know how to handle. And so that's why partial fractions is useful, because it helps us write it in terms of things which we have on the table. And then the last step is to take the inverse Laplace transform and get our function that we want. So let's work through one example. And hopefully we have enough time that we can finish this before class ends. So, no, we're going to finish it. We'll have at least 5 minutes left. I'm confident. So here we go. Beginning to end. X double prime minus x prime minus 2x equals 10 sine of t. That's our differential equation. Not homogeneous, so that's cool. Constant coefficients, no problem. We have initial conditions x of 0 equals 10, x prime of 0 equals 9. Now, you might say at the beginning before we start, do we actually have to use Laplace transforms to answer this question? And the answer is no, we can actually do this. What we're seeing is that there's this different approach. And there are reasons why Laplace transforms are nice in working with particular differential equations. We're going to see it more as we go on and develop more tools. But we want to see that it does work. So let's start with this one. Okay, so let's go through the process. What's the first thing we should be doing? Yeah, take the Laplace transform on both sides. See, it even tells us, step 1, do this. So we'll just do it. So we're going to take the Laplace transform of both sides. So Laplace transform of x double prime minus x prime minus 2x has to equal the Laplace transform of 10 sine of t. And that just says if two things are equal, the Laplace transforms are equal. No surprise there. We use the fact that Laplace transforms are linear and say, hey, this is really the Laplace transform of x double prime minus the Laplace transform of x prime minus 2 Laplace transform of x. And that should equal 10 Laplace transform of sine of t. Okay. Let's go through and work on simplifying. So, what can we do with this first part? What does it become? And here's where we go to our rule. If we're taking the Laplace transform of the second derivative, it's s squared times the Laplace transform of the function, and then there's these other pieces. Minus s times what happens at 0, minus the derivative at 0. So, this part would become s squared, that's because second derivative, and then we would have our function x of s, because that's what we're calling the Laplace transform of x. And then we have to do some corrections. So we have minus s, function at 0, minus x prime at 0. So that's the first part. Then we go to the next piece. Minus, and we have a rule for that, to how to take the derivative. So the derivative, it's s times what we'd want, or just a function, minus the f of 0. So minus, I'm going to put parentheses here, because parentheses help save points, and we want all the points. That's our goal. Got to get them all. So s times x of s minus x at 0. And then the last part will become what?
Needed to x of s.
Yeah, so that's just exactly what we're after. Minus 2x of s. Okay, so that's what happens when we clean up the left-hand side. We still have the right-hand side. So the 10, that's great. That's just 10. Do we know the Laplace transform of sine of t? So for that, we don't rederive it. We look at our chart and say, does sine of t show up anywhere? Yeah. Shows up down here. So what's the Laplace transform of sine of t? Yeah, so in our case, it'll be 1 over s squared plus 1. Okay, so 1 over s squared plus 1. All right. Now, we're almost there. We should do a few things. What is x of 0? 10. We'll replace that. And what is x prime of 0? 9. Okay, at this point, we've successfully finished step 1. So step 1 is done. So now, we're into step 2. So for step 2, we need to get x of s by itself. So let's gather what's in front of the x of s's. So we have s squared minus s minus 2. And you might be thinking, hey, that feels kind of like s squared minus s minus 2. Feels like the kind of thing we would normally do with these kinds of problems. And it's not a coincidence. What else do we have? Minus 10s, minus 9, and plus 10. So it makes plus 1. And that's everything on the left-hand side. Right-hand side is 10 over s squared plus 1. Now our goal is to get x of s by itself, because that's what it means to solve for x of s. So what do we do now? We'll bring this across. So we're going to move it across. It'll become plus 10s minus 1. Now, the next thing I want to do is I actually want to put this together. So I'm going to combine this so it's just one big piece. And it may not seem the most obvious thing to do. And hopefully I'll justify why in a few minutes. But I'm going to do it right now. So if I wanted to add these two pieces together, what would we need to do next? Yeah, we want to get a common denominator, so multiply the second term by s squared plus 1 over s squared plus 1. Okay, so we have s squared minus s minus 2, x of s is equal to s squared plus 1 is our common denominator. What's the highest power we're going to get here? S cubed. How many s cubes do we have? 10s cubed, because we have 10s times s squared. So 10s cubed. What's our next highest power? Okay, s squared. How did we get that? Okay, so that means a minus s squared. Okay, what's next? There's a 10 times s. All right. And anything else? There's a minus 1 plus 10 making plus 9. S squared minus s minus 2. Can we do anything with that expression? We can divide it over. Yes. What else can we do to it? Does it factor? And if it does factor, how does it factor? S minus 2, s plus 1. And then we'll divide it over. So we see that x of s is 10s cubed minus s squared plus 10s plus 9 divide by s squared plus 1 times s minus 2 times s plus 1. Okay, that's step 2. Okay, so we're now done with step 2. Now, I have to pause for a second and say, did we have to actually put these together? The answer is no, you didn't have to. But you'd want to, for the following reason. If you didn't combine them, you'd have two pieces. And then what would happen is that on each piece, you'd have to do a partial fractions problem on each piece, which means you'd have to do two partial fractions problems. And that's 2 times more than you want. It's actually probably a lot more than 2 times more than you want. But by combining to one part, you only will have to do one partial fractions problem. So that's why I put it together. Now we come to step 3. We have to simplify this, pull this apart. So, what can we do? Yeah, this feels very familiar. 10s cubed minus s squared plus 10s plus 9. S squared plus 1, s minus 2, s plus 1. It's almost like we anticipated that this was going to happen. So this, what you see here, this is step 3. So that was pretty quick. Check. So I'm going to copy the answer here. Now, keeping in mind that we want to end up with things which are things we can take the inverse Laplace transform of, is there any modification to our answer we want to do? Any modification at all? Hint, there's a modification. If it helps, I'll just randomly tap on something as though to indicate this is where you might be thinking of where to think about where the modification should be. Separate them. What do you mean by separate them?
Like s over s squared plus 1 minus 3 over s squared plus 1.
Brilliant. Why do we want to do that?
So that it matches something on our table.
Yeah. See, s over s squared plus 1 matches something on our table. 1 over s squared plus 1, I don't need to worry about minus 3. Minus 3 is 1 for all intents and purposes. Over s squared plus 1 matches our table. But s minus 3 together doesn't. So we're going to have this as s over s squared plus 1 minus 3, I'll just pull out the constants, 1 over s squared plus 1, plus 7 times 1 over s minus 2, plus 2 times 1 over s plus 1. Okay, that's x of s. Now we come to step 4. Take the inverse Laplace transform. So this is where we get to use our table. So, well, we've already been using our table. The inverse Laplace transform of x of s is x of t. Now we start scanning our table. Do we see anything that looks like an s over s squared plus 1? So that becomes cosine. So, cosine of t. How about 1 over s squared plus 1? Yeah, what is it? Sine. So don't forget there's a minus 3 attached, so minus 3 sine of t. S minus 2. Casually move this over as though trying to look super casual. E to the 2t. So plus 7 e to the 2t. 1 over s plus 1. Yeah, so plus, you can think of this as s minus minus 1. So it'd be plus 2 e to the negative t. Okay, good. We did it. We made it all the way through. Woohoo! It worked. It worked. Great. Okay, now, so we should check. Any questions about what happened? I don't think any one particular step is too bad. It takes time in some of these steps. I will say, why do I think Laplace transform is a good thing to do? And for me, it comes down to it does a great job of handling initial conditions. Because at the end, we didn't do much with initial conditions, because the initial conditions were baked in at the start. And so that's why I like to have the Laplace transform, is because the initial conditions, they show up here, and then we never have to think about them again. It all works out in the right way. All right, well, we have 5 minutes left and 3 more problems to do, and they're all about the same length. We'll just start with the next one. We probably won't finish, but let's at least get the idea out. Just in case you might see something like this, say on a homework assignment. Use Laplace transforms to solve the following system. So now there's multiple things we're trying to solve for, not just x, but x and y. We're told x of 0 equals y of 0 equals 0, x prime of 0 equals y prime of 0 equals negative 1, x double prime plus 2x plus 4y equals 0, y double prime plus x plus 2y equals 0. All right, so that's what we need to do. Okay. Now, we haven't actually said explicitly what we should do, but let's just think about the intuition. It's same processes, so how would we start?
Get all of the x-terms by themselves on one side.
Someone says, let's take the Laplace transform. Okay. Now, there's a good clue that we should probably take the Laplace transform. It's called, it tells us to do it. So that's a great clue to pick up on. Now, you might say, but wait, we have two things we're trying to solve for. That's okay. So what we can do is instead of just, we have x of s, that's the Laplace transform of x of t. But what else can we do? We can do y of s. And that can be the Laplace transform of y of t. So now we're going to have x and y. So we'll take the Laplace transform of both sides. Now, on a side note, what's the Laplace transform of 0? Yeah, so we'll just leave those as zeros. Okay, so we have the Laplace transform of x double prime plus 2 Laplace transform of x plus 4 Laplace transform, whoops, I almost forgot how to write fancy y, equals 0. And, of course, the second formula, Laplace transform y double prime plus Laplace transform of x plus 2 Laplace transform of y equals 0. All right. Well, let's go through piece by piece. Laplace transform of x double prime. What does that become? S squared x of s, good, minus s times x of 0 minus x prime of 0. Okay. The next piece, well, that's just straight up, nothing fancy, capital X of s. And then we have 4 capital Y of s. We can do the same thing on the next line, but the next line, the really only difference with the first thing is instead of x, we have y. So we have s squared y of s minus sy of 0 minus y prime of 0. Then we have plus capital X of s, and then plus 2 capital Y of s. Okay, does anything simplify?
Yeah.
What?
All of the x of 0 and y of 0 is a 0.
Good. That helps. Right. So this is -1, -1. Okay, so now what we can do is we'll group. So we have two terms with x of s. We can say s squared plus 2 times x of s plus 4 y of s. That equals -1, because I can move the -1 across. And then downstairs, well, we have a single 1 times x of s. Then we have s squared plus 2, so plus s squared plus 2 y of s. And again, equals -1. And now, what do we see here? Well, we see two equations and two unknowns. Ah, our classic bread and butter type of stuff. So, what can we do? Well, the answer is we can do lots of things. But we can now solve for x and we can solve for y. So, as an example, one way we can do it is we could use Kramer's rule. You don't have to use Kramer's rule, but you can. So, if you did, and I think this is how the book likes to do their example. So by Kramer's rule, do you want to solve for x or for y? X. So you'd say x of s, it's a ratio of two determinants. Downstairs, it's your coefficients. Upstairs, it's similar, except you replace the first column by the minus 1s. And so what you end up with, well, taking your determinant upstairs, you get minus s squared plus 2, multiplying down, subtract minus 4, which really means plus 4. And then downstairs, you'll get s squared plus 2 squared, subtract 4. Which, if you clean this up, this is minus s squared plus 2. If you square this, you'll get s to the 4th plus 4s squared plus 4 minus 4 is 0. And that becomes minus s squared plus 2 over s squared times s squared plus 4. So that's x of s. Now that would essentially be after the second step, right? Because you solve for x of s. After this point, what would you do? So let's just spend 30 seconds to talk about the game plan from here. We won't finish it, but what happens next? Partial fractions. How many pieces in the partial fractions will we have? He asks us, he draws 3 pieces. Yeah, we'll have 3 pieces. What goes down here? S squared. You got to build your way up. S squared plus 4. A, B, and CS plus D. And now you work partial fractions to solve for A, B, C, and D. And then once you have them, you would take the inverse, and then you'd have your x of t function that you want. Do the same thing for y, and you're done. All right, we'll do more examples next time. Have a great day.